advantage. So the advantage number 1, the number of transistors is n plus 2. To implement this versus 2n for, right? So this is, so number 2, each input sees only one transistor. Why? If input signal in case of CMOS, static CMOS, is going to pull down and pull up, right? So if I want to implement this using static CMOS, right, then I will have a pull down block, I will have a pull up block, right? And then this input A will have one here, one here. So the electrical load for every signal line corresponding to A will be one NMOS transistor here, one PMOS transistor here in case of CMOS, static CMOS. But in case of n-type dynamic, whether it's n-type dynamic or p-type dynamic, it will only see one single transistor as the load. As a whole, the input will see only the parasitic capacitance of one transistor. So when the parasitic capacitance on this line is less, it can be raised and lowered. The switching here from 0 to 1 and 1 to 0 can be much faster. So each signal line will see much less capacitive load, less than half, because for n-type dynamic, this is not seeing a PMOS transistor over there, and PMOS is 2 to 3 times larger. So it will have much larger capacitance than this single NMOS. So if I compare this n-type dynamic with this static CMOS implementation, this input signal switching speed will be much faster because it will see less than half capacitance. So that means n-type dynamic or p-type dynamic circuits will be faster because it says lower capacitance, faster, and overall the number of transistors is less, circuit complexity is less. So since number of transistors is less, so you will have less wire going through the circuit. So circuit resources will be less. So you can expect that it should consume less power compared to its static counterpart. However, in static counterpart, if there is no signal change in the input side, the circuit does nothing. It sits idle. But in dynamic circuit, at every clock cycle, it switches from pre-charge, evaluates, pre-charge, evaluate with the clock signal. So there is a guaranteed clock switching in every clock cycle for these two transistors, even if you are not changing the input. So due to this additional guaranteed switching of clock signal, it does not consume significantly less power compared to its static counterpart. So it is less but still almost equivalent. Sometimes depending on the switching activity, it can consume more power. But overall, because of the lower complexity, lower number of transistors, lower number of wire, less area, overhead. Because more transistor means you need more wires to connect. So on the chip, you will have more area for that one compared to this one. And chip area is the most expensive and valuable resource you have, right? So these are the advantages. Now also let's look at the other thing from noise point of view. It can produce full swing signal. What does it mean? When clock is 0, it is precharged. It is disconnected here. So VDD is connected to the output, and this is a PMOS. PMOS is very good at pulling up. So this can pull up all the way to perfect VDD. During the evaluation phase, this is on, this is off. If this signal turns on the pull down network, it gets connected to ground. This pull down network is made of NMOS and it is very good pull down, so it will go all the way down to 0, producing perfect 0. That means entire dynamic circuit like static CMOS can produce perfect 1 and perfect 0. So that means its VOH is equal to 1, which is VDD, which is perfect 1, and VOL is equal to 0, which is perfect 0. So that means voltage swing is the difference between these two. So it is full voltage swing because it is VDD. So these are the advantages. Now, some of the challenge or anomalies, let's look at those. Constraints or disadvantage. Number one disadvantage is this circuit is asymmetrical. During the evaluation phase, let's say pull down network does not turn on, then output is already precharged to 1 and it will be floating 1, because in the precharge evaluation phase this is off, so output is disconnected from VDD. If this pull down network is off during the evaluation phase, it is also disconnected from the ground, so output will be precharged to 1, but it will maintain that 1 in floating state across this capacitor CL. So the number one problem of dynamic circuit is floating node. During the evaluation phase, for half of the cases, it will be in floating state, because statistically we know that for some input combination the pull down will be on, for some input combination the pull down will be off. Whenever the pull down is off, the connection to ground is disconnected, the connection to VDD is already disconnected in the evaluation phase. So for every time, every input signal, if the pull down network is off, output will be in floating state. If you keep any signal in floating state, then it is unprotected. That means any noise can distort this signal and push the value in the undefined region. Yes.
After the F, it's V80.
V out actually. V out. V out. The output node, the node voltage. So the second disadvantage of this is it is noise sensitive, right? Because it is very vulnerable to noise. Because in floating state, it is not guarded by supply or ground connection to protect is 1 or 0. So it is very vulnerable to noise. So the noise margin will be very low. So it is. So that's why dynamic circuit cannot be kept in floating state for a long time. It needs to be refreshed periodically so that we don't lose the data. And the number 3 disadvantage is the design is asymmetry. In the precharge phase, it is already precharged to 1. If the pull-down network is not on, that means for that input combination, output should be high during the evaluation phase. But that output is already high pre-charge. So you will not have any time needed for TP-LH. Typically, when pull-down network is off, output should be 1, that means outputs will have a transition from low to high. But in this case, before we even enter into evaluation phase, during the pre-charge phase it is already 1. So the moment we turn off the pull-down network, the desired output 1 is already there, so TP-LH is equal to 0. And then during the evaluation phase, if the pull-down network is on, a connection is established. This clock in the evaluation phase is already on. So a connection is established from output node all the way to the ground. However, now it will take a high to low transition, right? It will make a high to low transition. That high to low transition, if I now compare with this static CMOS, let me draw it up here. This is pull-up network. This is pull-down network. This is like static CMOS, right? So TP-HL, high to low, will be the time output takes to be discharged to the ground through the pull-down network. Now, with the pull-down network, we added 1 extra clock transistor. So it has to travel through 1 extra clock transistor connected in series. So the TP-HL, high to low transition time, will be slightly longer because your path length is increased by this transistor. So this one, it will be higher than TP-HL of static circuit. So the design is asymmetrical. Why? Because TP-LH is equal to 0, TP-HL is larger than static CMOS, right? And here always TP-LH less than equal to TP-HL by default, so it cannot be symmetrical. So it is always asymmetrical. So these are the major advantage and disadvantage of dynamic circuit. But still, for certain application, dynamic circuit has become the default choice, particularly for RAM industry. For RAM, it is predominantly DRAM. Static RAM are used for few applications. Why? Because memory is the most densely populated circuit in your microprocessor. Whether it's an on-cache memory or on-chip cache or off-chip RAM or other cache, memory circuits are the most densely condensed circuitry in any microelectronic application. So you have so many memory cells, billions of memory cells are arranged in rows and columns. So if you can save 1 transistor per memory cell, you are saving 1 billion transistor in case of a 10 gigabyte memory, right? So that's why this one, n plus 2 versus twice n, the savings of almost 50% of the transistor for a 10 transistor circuit is 20 plus 12 versus 12, right? So that is the biggest advantage of dynamic circuit, ability to implement any logic or memory circuit with significantly less number of transistors, consuming less area inside the chip consuming less power and also giving higher speed, because less transistor means lower parasites. So you can also do the pre-charge. Now same example, if we now draw p-type dynamic, what will happen? P-type dynamic, same one, AB in parallel series. So here then I have AB in parallel, right? Series with C. Then this is output. I think I need to borrow one more. Is it the right one or it is not the one? You gave me? Oh. So PMOS, 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 PMOS. This is VDD. This is block A, B, C. We are drawing p-type dynamic AB plus C, right? This is p-type dynamic. For this one, recharge phase will be clock equals to 1. Evaluation phase will be clock equals to 0, and its recharge value will be 0. When clock equals to 1, this is on, this is off, it will be recharged to 0. During the evaluation phase, clock is 0, it will be off, it will be on. Now, depending on the input's ability to turn it on and off, if the, yes.
Isn't the output supposed to come from the top of the pull-up network?
No. Always output comes below the pull-up network.
Oh.
Yeah. So output, no matter what is the circuit, static or dynamic circuit? Okay. That's fine. So, if the pull-down, if the input turns on the pull-up network, this is our pull-up network, then output has a connection to VDD because in the evolution field is on, so output will be have a low to high transition. So this low to high transition now will be equal to low to high transition of a static circuit plus delay of a, like that one, delay of a clock, right? I am just writing in a different way, same thing over here. So this is the pull-up network, TPHL for static, because in static only this pull-up network will be there. We are adding a clock in series. So this TPHL will be, so TPLH of P-type dynamic will be TP as H of static. Similarly, using the other one, TPHL, high to low, will be 0. Why? In the evaluation phase, this clock is off and it is already pre-charged to 0. It is disconnected. If the pull-up network is off, it is also disconnected from the supply. So output will have the previous pre-charge value of 0 in floating state, disconnected from the ground, disconnected from the supply. So P-type dynamic will have a floating state for output 0, right? So here floating state is when output equal to 0. For that one, floating state is when output equal 1. So TPLHL is 0 for this one. For that one, TPLH is 0 because here it is already P-charged to 0. So all other things are same. So now, if you have learned how to draw static CMOS, then you can draw P-type and N-type dynamic circuit any way you want.
So the floating state unavoidable?
Yeah, so for P-type dynamic circuit, when the output is 0, it is vulnerable because that output is in floating state.
Yes.
So that's why you have to quickly refresh it. Because if you keep it in floating state, 0 in this case, if a noise is injected, that noise cannot be basically taken care of. You cannot kind of vanish that noise because it is not connected to supply or ground. Same thing in the floating state of 1, a noise can be injected, it can push it below 1 or above 1, and then there is nothing to save that noise from the permanent distortion. And the other thing is that whether it's floating 0 or floating 1, one of the common parasitic effect in any electrical circuit is it will always have a leakage. There is nothing called ideal electrical circuit. So if you keep an electrical node unprotected, unguarded, in floating state, no connection to supply and ground, if you leave it for a long time, all those parasitic leakages will gradually eat away your stored charge and destroy your logic circuit. So that's why in floating state, when you are maintaining an output high, actually signal does not stay at high. Output signal goes like this. Before it goes below the noise margin high, if it is below noise margin high, then you lose the signal, right? So that's why you have to refresh it again. So that's why the clock signal of dynamic circuit must be short enough so that if your clock signal is like this, a long clock signal like this, what will happen? Depending on whether it is a P-type dynamic or N-type dynamic, it will be floating here or here. Evaluation will be here or here. And in the evaluation phase, it will be floating. Let's say it is floating here. And you want to have you are supposed to have a high output. And if this clock period, so entire duration of clock equal to 1, you have a high output, that output ideally should stay exactly high for the duration, but practically it will basically go down like this. So if noise margin, let's say noise margin high is here. If it goes below noise margin, there is no longer high signal. It's in undefined region. So I cannot keep the clock signal up here. I have to bring the clock signal here. I have to shorten it so that it cannot go below the noise margin.
Now when you say so for
This is I'm just
so
not nothing to do with this one. I'm just saying the general. Let's say a particular circuit, that's an N-type dynamic circuit, is in evaluation phase.
Okay.
Evaluation phase is clock high.
Okay.
And clock high means evaluation phase. At that stage, you have an input which produces a floating output. We have seen that for certain input, you can have a floating output. If the output is floating and high, ideally the output should stay high for the entire duration of evaluation phase. Evaluation phase is when clock is 1 for N-type dynamic. So this is the whole evaluation phase when clock is high, from here to here. And for entire duration of evaluation phase, output should remain high if your input produces a high output. But because it is floating, there is no connection to supply and there is nothing to guard that, leakage and noise will gradually deplete that charge stored at the parasitic capacitance at the output. So it will gradually go down because leakage is always there, noise is always there. So now, can we allow it to go down all the way below the noise margin? No, because then you lose the signal. So I have to shorten the clock period length so that this floating output signal doesn't get enough time to go below the noise margin. That means every dynamic circuit must be operated with a minimum frequency. Minimum frequency means maximum length of the clock period. If the clock period length is longer than that, the floating output will have enough time to go down below the noise margin. So that is one of the important requirements for dynamic circuit. Every dynamic circuit must minimum clock frequency of operation. If you design a circuit and you operate the circuit below that clock frequency, then your circuit will malfunction. So this is an important distinction between static circuit and dynamic circuit. Dynamic circuit can be synchronous, frequency enabled, or asynchronous. It does not affect its operation. But in dynamic circuit, it has to be always controlled by a clock signal, and that clock signal must have a minimum clock frequency based on the design parameter and the voltage it accommodates from the output. If the frequency is below that, clock signal will be long enough for it to have enough time for the output to be distorted.
So is the clock is what's connected into VDD or ground, or the input? What's the inputs?
No, the clock is connected here. Clock is connected here. So here, this periodic pulse of clock signal is connected to this end.
Right.
So precharge is 0, when clock is 0, evaluation for clock is 1. So for this half of the clock signal, when clock is 1, this one will be on, this one will be off. So output is disconnected from the supply. Now output can only have one possibility, because this is on, it can have a connection to ground. However, if for a given input combination, let's say A equals 0, B equals 1, C equals 0. For this input combination, it is disconnected, so output is disconnected from the ground, output is disconnected from the supply already because clock is high, it is off, this is on. So output is in floating state. Output is in floating state for how long? As long as this clock is off and this clock is off. How long this clock will remain off? For the entire duration of clock signal high. If that clock signal high, that duration is much longer, this node will remain in floating state for much longer time. So the leakage, the noise or whatever, all the disturbance can chip away, can distort this output signal, right? And this output signal, instead of remaining at high, it will gradually go down. But if you think about the signal strength, highest possible is VOH, the lowest possible is VOL. And here, there is a limit called noise margin high. Here, there is a limit called noise margin low. Only this is valid 1, only this is valid 0. If leakage and noise distorts the signal and brings down noise margin high, then you lose the signal. There is no longer a meaningful signal, right? Your circuit will malfunction. So we cannot let this node to remain in floating state and experience leakage for a long time. If we do that, then it will come down below noise margin high and lose that binary 1 signal. So how can we prevent this node from having long period of floating state? by shortening this clock period. So how short? Short enough so that the decays cannot bring it below noise margin high. So that's why the clock period length cannot be certain limit. That means frequency cannot be below certain limit because frequency is reciprocal to clock period. That's why it is an important critical design requirement for dynamic circuit that it must be operated with a minimum clock signal. So then you basically look at the other examples, and the other thing we want to highlight another, in addition to floating node problem, there is another potential which is more prominent it is present in static circuit, but it is very dominant in dynamic circuit. Let's talk about it. It's called charge sharing. Another biggest disadvantage of charge sharing noise is called charge sharing noise. This is the charge sharing noise is present in any electrical circuit, but it creates a huge problem for dynamic circuit. Charge sharing noise. So let's say we are talking about evaluation phase. In the evaluation phase, this clock is off, this clock is on. Before we reach evaluation phase, in the pre-charge phase, this output is already pre-charged to 1, right? Now, let's say I have an input combination A equal 1, B equal 0, C equal 0. Right? Among many possible input combination, I have an input. For this input combination A1, B0, C0, this path is off because this is off, this transistor is on, this path is off, so this will not have a high to low transition even though this clock is on. For this input combination, output should be high and it will remain at floating high because it is disconnected already from here. This path is off, this path is off. However, for this input combination, transistor A is on. Remember, there is an internal node capacitance. Now, for this input combination, yes, output will not have a high to low transition, but this internal node capacitance now comes, it becomes connected with the output node. An empty bucket now is connected with the full bucket. So what will happen? There will be charge sharing, charge distribution. This capacitor will inject some charge into this. How long this charge sharing will go on? As long as both of them come into the same height of the charge. So the output here will go below 1 and this one will be charged above 1, above 0, and they will meet across. So even though for this given input combination output should remain 1 because pull down network is off and there should not be any high to low transition. However, because of the in the series path which transistor is turned on for which input combination, this internal node capacitor will come into play and it will take away or share some charge from this one. As a consequence, this will be distorted. So this AD distortion is a noise, and that's why it is called charge sharing noise. In this charge sharing, the magnitude of charge sharing, let's say this one is completely empty and it's a large capacitance. It can take away half of its charge, pushing this value right in the middle, somewhere here, then you lose your binary signal. So, and why it is vulnerable? Because at that stage it is floating. Circuit charge sharing will happen, but the good news is in steady circuit, whenever there is no high low transition, there is a path to VDD. So, even if it shares some charge out of it, that static VDD connection will replenish, refill that charge, so it will maintain perfect one. But in dynamic circuit, in evolution phase, entire dynamic circuit is disconnected. If it is distorted by sharing with this one, there is nothing to refill it. So that's why charge sharing, there is internal redistribution. Charge sharing means internal redistribution or internal sharing of charges between node output capacitance and internal capacitance. This thing can happen in any electronic circuit, but in regular static circuit it's not a problem because VDD is there to refill it. But in case of floating dynamic node, there is nothing to refill it.
That's a question real quick.
Yes.
So just for the operation wise, on this N-type dynamic, at the pre-charge stage, clock is 0, the V out is then set pre-charge to 1 because
yes.
it's connected to VDD, correct?
Yeah.
And then at clock is 1, evaluating based on the inputs, V out can change between 0 and 1.
Yeah.
But if it's kept at if the inputs don't connect to the ground,
Output should be by default 1.
stay 1 and float
Yeah.
at that point.
So
Okay.
logically, if any input combination does not turn on the pull-down network,
Mhm.
for that input combination, output should be 1, high.
Okay.
Yeah. Logically, if pull-up network is on, then output is 1. If the pull-down network is off, output is 1, and the vice versa. So, you can now, for this type of charge sharing node, if this circuit is sensitive, that we cannot experience, we cannot have distortion here because of charge sharing, how can we prevent? Because when you have, this is a 3-input circuit, right? We cannot guarantee that this input combination will never appear. It will appear 1 out of 3 every 3 times, right? So, and if this output node is very sensitive, then there are some technique called keeper technique to prevent this circuit. One of the keeper technique is to put one additional charging transistor with the VDD. So basically also this is connected by clock. During the pre-charge phase when clock is 0, so it's basically providing one bypass path to this intermediate node. It's called keeper logic. So during the pre-charge phase when clock is 0, this is on, this is on. This node is pre-charged to 1, all the way to 1, this capacitance. Because of this connection, this internal node capacitance also will be pre-charged to 1. Now, for this input combination, even if this transistor is on, no charge sharing will happen because in pre-charge phase, we charge both of them to VDD. So both capacitance is fully filled up to VDD, so there will be no distortion or distribution taking place. So if the circuit is very sensitive, you cannot tolerate any internal charge sharing, then internal node should be protected by this additional path to recharge it to up to the value equal to V out. So that is called keeper logic, or different types of combination you can actually have in the keeper logic. But yeah, there's this small solution.
I have a question.
Yes.
At evolution phase, this transistor is also off, right?
Yeah.
At evolution phase.
Evolution phase, because if I drive it, this is a PMOS, if I drive it in the clock, so both of them will be off, so it will not disturb pull down operation.
In that case, the features evaluation test, there is still a path between this V out this internal capacitance and the recharging is happening, right?
So now in the evaluation phase, I know what is getting. So in evaluation phase clock is 1. So this transistor is off, this transistor is off. Only this one is on. So if this transistor off, this is just an open circuit, it is open circuit. So there is no, so this internal node capacitance is connected downward, right? So if I have a high low transition to A and B, while I am discharging output, I have to discharge this internal node capacitance anyway, right? Even if we don't have this keeper logic, we have to, if you turn on this path for high to low transition instead of this one, you have to discharge this capacitance plus this capacitance, right? So it will not, this addition of keeper logic is called keeper logic or keeper clock or keeper transistor. It will not disturb the operation of pull down network when it is making a high to low transition. It will only aid in the precharge phase by precharging this internal node capacitance exactly same voltage of the output voltage. So in the floating state, when both are high, there will, if it is on, there will be no internal sharing. So, and there are many other combinations of these productive techniques for charge sharing prevention. And the other third problem in dynamic circuit is, let's say you have this circuit, the third noise problem. So we have one noise problem, leakage, that distorts the floating node. So the number one source of distortion is leakage. Second one is charge sharing. If you do not, it is not clear, you can ask again. Number 3 is the noise problem in dynamic circuit is coupling capacitance, or it is also called coupling noise. So let's say this circuit is driving an inverter or some other logic circuit, right? Let's say it's driving some other logic circuit. So now, as you can see, every transistor has 5 capacitances between its terminal. So between, this is its drain terminal, right? And this common drain terminal is for this transistor, and for this wire, which is input to the next one. So there will be capacitance between this node and this node. There will be capacitance between gate and this. There will be capacitance between this. There will be capacitance between this. There will be capacitance between this, right? Every pair of transistor will have capacitance. There will be capacitance here, right? So let's say you are maintaining, for a given input combination, you are maintaining a floating high here. But high will produce a low signal here, so it will bring it down, right? So this side of the capacitance, now think about this. This node with this gate node, there is a capacitance, because this node is the gate terminal of this transistor. So this side is VDD, this side is making a transition from 0 to VDD to 0, because it is going down. So across a capacitor, if one side is stable at VDD and the other side is making or VDD to 0 transition. Then between them, electrostatic coupling will take place, and AC noise will create. It will inject charge from this direction. Or if it stays at 0, and this one is making a 0 to VDD connection, it will inject charge in this direction. In this case, it will inject charge in this direction. So the other side, this one is supposed to be stable at VDD, while this one is making a VDD to 0. But since it is making a transition, other side of the capacitor, it will experience oscillation. That is called electrostatic coupling or capacitive coupling. In case of a static circuit, if anything happens, distortion, this supply should refill that, take care of it. But in floating state, because of signal activity in somewhere else, this parasitic capacitance will impose some distortion here through coupling through the parasitic capacitance. In a static circuit, it is not a big problem because this node is protected by steady state connection. But when it is floating state, there is nothing to prevent it from any noise injection injected this way. If noise is injected this way, it will go above VDD. If the noise is injected this way, it will go below VDD. And that distortion cannot be refilled because it is connected to the gate, and gate is insulated and it is floating. So that is the third most important noise source or types of noise in dynamic circuit. So dynamic circuit suffers from three types of noise. One is floating leakage noise, one is charge sharing noise, what we have discussed, and the third one is capacitive coupling noise because of the presence of all the parasitic capacitance inside the device structure. So one of the common, and there is a special case of coupling. So now this is the clock transistor, right? And this is a particular transistor. This is internal node. So between this node there is a parasitic capacitance, right? Because gate terminal of this transistor to the drain terminal of this transistor, there is a parasitic capacitance. Now, in any given circuit, input signals may not change for 5 clock periods since you are not doing anything. But as a dynamic circuit, these 2 clock signal will not remain idle. It will always oscillate like this, right? It will continuously oscillate. That means even if this whole pull-up network is idle, not changing the input for 5 clock periods, but during this 5 period, this one is going up, down, up, down, up, down every clock cycle. That means it will either inject this way or that way charge into this node, right? What if this is the output node? Because this one will have a capacitance with this one as well, right? So while you are not doing anything here, output should remain at a steady state. But this parasitic capacitance coming from the clock transistor to output here, this one is changing like this, right? So it will disturb the output. So that's why the output, instead of even the clock signal itself, you should get a periodic clock signal like this, but due to parasitic capacitance, it may inject noise into it or it may inject noise in the opposite direction. So as a consequence, your clock signal will look like this. Because it will be injecting noise every time it is making a transition in the opposite direction, there will be noise injection in one way or the other. As a consequence, the clock signal itself will become distorted, and that is another special case of capacitive coupling or electrostatic noise, and that is called clock feed through. Clock feed through. It is in the slide. There is a special noise problem in dynamic circuit. So another challenge of dynamic circuit is cascading problem. Do you have another one, black or blue?
Yes.
I won't report you for stealing. Which class you are TAing?
Microprocessor,
Oh,
the lab.
well, you need all those. Yeah. So, along with all those disadvantages and challenges, now let's add one more disadvantage, number 5 or 6, that is called cascading issue. What is cascading? In many logic circuit, we may have to connect multiple logic gates in series one after another to build complex logic circuit, right? Just it can be AND gate or gate or whatever. But in case of dynamic circuit, if I connect this is PDM. Let's draw another one. So this is output. Let's say output of this one is connected to the input of this one. And then final output. So what happens here is in the recharge phase, this should be recharged to 1. If this way, this also recharged 1, right? So in the recharge phase, we are not evaluating. So both recharge 1 doesn't pose any logical problem, right? But actually, any CMOS circuit is inverting by nature. If the input is high, output should be low. If input is low, output should be high. But in the evaluation phase, let's say this pull-down network does not turn on. That means it should be 1. In that case, it should be 0. But if it turns on, it will be 0. Then, if it is 0, it should be 1. But the problem is then, in the evaluation phase, initially this is 1, this is already on. In the evaluation phase, when this is on, then it will get a path to ground. In the evaluation phase, when you are trying to achieve a 0 here, this should stay at 1, right? But when it was 1, it is already on. In the evaluation phase, it is on. The moment it is on, it gets a path, so it is discharging to 0. You are trying to set this to 0, and logically that should set this to 1. But both are n-type dynamic, same pre-charge, same evaluation phase. When you turn it on, this is also on. So it will discharge. Logically, when you are trying to set this to 0, it should remain at 1. So that's why cascading, because their evaluation phase and pre-charge phase are identical, cascading an n-type dynamic with another n-type dynamic is forbidden. Because in some output-input combination, you will not get the desired value. because you lose it before you can set it, right? Because they have identical evaluation, and that's why to prevent this, we have to make sure that if this one is in pre-charge phase, this is an evaluation phase. If this one is evaluation phase, this one is pre-charge phase. That's why N-type dynamic must be followed by a P-type dynamic. It cannot be N-type and N-type. It is forbidden, it is permitted. So cascading of two N-type dynamic, identical N-type dynamic circuits is forbidden. But cascading, if you need to do, you have to put an N-type with a P-type, N-type, P-type.
And P-type, P-type?
Yeah, NP, NP, or PN, PN, whatever. So that means the consecutive blocks of dynamic circuit, if you need to cascade more than one block, consecutive blocks must be of opposite type. To make sure that when this one is pre-charge, this one is evaluation, when this one is evaluation, this one is pre-charge. So that accidentally they don't destroy the value. Yes?
So in the first CMOS circuit, PDN pre-charge value is 1.
Yeah.
In second, we are expecting pre-charge value should be going to 0.
0. Yeah, so that's why if you are setting it 1, it will be 0. If you are setting it 0, it will be already 1. So you don't have to. And good thing is when you are evaluating it, it is in pre-charge phase, so nothing will happen here. Right? So that's why we want to basically take advantage of their opposite characteristic to safely cascade them with one another. Now, because it is prohibited to cascade an N-type dynamic circuit with a P-type dynamic circuit, sorry, N-type with another N-type, so a solution is domino logic. A solution is domino logic. What is domino logic? Domino logic is an N-type dynamic followed by an inverter. So this inverter provides an electrical isolation. So together, an N-type dynamic block, together if you put inside the box, it is called domino logic. And you can cascade this type of block, 100 of them one after another, without problem, because in between there is an inverter, static inverter, isolating them electrically. So one side will not disturb the other. So the domino logic is not a new logic. It's just an N-type dynamic followed by an inverter. So what is the advantage and disadvantage of domino logic? So at the output, you would always get uninverted form, because this inverter, so let's say if you are implementing AB plus C, not whole part, right? Here you will get AB plus C. Inside this node you will get AB plus C whole bar, right? So the domino logic will implement any logic circuit directly in an inverted form, because it has an embedded inverter inside it. So domino logic is not a new logic style. It's an N-type dynamic circuit followed by an inverter inside the box. Why it is called domino logic? If you connect X number of domino logic, which is an inverter, with N-type dynamic inverter, N-type dynamic 1. If it produces a 1 here, it will produce a 0 here, and it will 1 here, 0 here, 1 here, 0 here, as if the signal is falling forward. It's a domino effect. The signal will go always alternate. So because of the way signal propagates forward, It's like a domino effect. That's why it is called domino logic gate.
You can swap it out for P-plane. That could be.
Typically, because you can do that, yes, theoretically you can do that, but domino logic they use only n-type because n-type clock is size-wise, efficiency-wise is much better.
Because it's increasing the length due
Yeah.
to the n node.
Yeah. So, and the other thing is, now, another special case of a dynamic logic circuit is called NP logic. NP logic also is not a new logic. It's basically, if you put an n-type and p-type dynamic circuit in one block, it's called NP logic. That means it is a logic which is implemented by alternating between n-type and p-type. That's why it is called NP logic. So it's basically the implementation style. It's not a separate logic style. So that's the end of lecture 5. This one, how many times? I have to turn it on. So,
This is the end?
this is the end of static combinational circuit. In lecture 5 we did, lecture 4 we did static CMOS circuit, in lecture 5 we did dynamic CMOS circuit, right? And then from lecture 6 we are going to do sequential circuit. So we will start it next day. Now let's talk about our makeup class. So after I got like 10 emails with various conflicts and proposals, so it looks like that finding an in-class, in-person common time will be very difficult. How about tomorrow via Zoom?
I have, day after tomorrow I have a meet.
Huh?
Day after tomorrow I have a meet.
Okay, yes.
I think you could probably get some people on the Zoom, but if you could record the Zoom and
Yeah.
then post that, that would help a lot of us that like work. and stuff.
Definitely.
Record.
I will record it anyway, but if I can get all of you on the Zoom, even in the evening, so that we can have some questions and discussion. So, Thursday, seven is okay for everyone. So Thursday, this Thursday, 7 p.m. I will send you the Zoom link. So be there, and I will also record the session and share the recording with you.
Can you shift it to
Hmm?
8?
Eh?
Shift it to 8.
Well, please, no.
Huh?
Like, can we shift it earlier?
Somebody is saying later, by the way. There's somebody saying 8.
So how about in the morning?
Huh?
What time in the morning?
I don't know.
Anytime. Anytime in the morning.
Huh? Okay.
No, in the morning I have a.
So 7 is, how many of you for 7? Raise your hand.
7 p.m.?
7 p.m.
7 p.m. I'm okay with it.
Okay. So majority 7 p.m. How many are you for 11?
11 a.m.?
11 a.m.
No, I'm a mid.
At 11 p.m.
I'm a
I'll
mid.
be asleep at 11 p.m.
Well, for me actually, for me later in the night is better because I do all my writing and everything deep at night. Like when everybody goes to sleep in my household, that's when I start writing. So let's do Thursday 7 p.m. and if needed, we will basically have another session. And the other thing is that I just want to make sure that I have enough time to explain everything. Okay? And those who have missed quizzes with prior permission, please contact TA. I already told him to give you appointment for those quizzes. And for one student who missed midterm exam with prior permission, I am going to email you. Most likely it will be on Monday.
What topic you will be covering?
Huh?
What topic you will be covering? The past classes or this topic?
What?
For the makeup class.
For makeup class, no, I will introduce lecture 6.
Hey, I got a question for you.
Lecture 6, sequential logic.
Hey, question.
Yes.
Hey, so last class, TA took attendance. He said he's gonna have a conversation about a little extra credit for a little point for us being here last class. Now, I wanted to see if he talked to you about that and see if, if that's still an option, because he took attendance on who's here, we stayed for a little hour.
Last week, I'm sorry for not sending the email that there will be no class on Thursday. But I asked, did the TA cover anything?
Nah.
No.
We went over our work here, though.
Yeah, so I'm sorry. I was on the plane actually. I was in Washington, D.C. From there, I went to Houston. So I was thinking to send him an email to come to the class and do some problem. But then in between flight transition, I completely forgot about it. So,
With that being said, that's a no, yes, yeah, little something.
well, let's say when I do the final reading, I see that you are missing a certain grade by 1 or 2 points, then definitely this factor will come into consideration.
Okay. Yes. Thank you.
Okay. See you.